Good afternoon, everybody. How's Ignite going so far? It's a good one? Yeah? Yeah? I mean, it's kind of like old times, isn't it? For those of you that have been coming to this for a while, finally large Ignite, big session rooms, and it's pretty awesome to be back here in person. So, welcome to Inside Cloud Native Incubations. In this session, I'm going to take you on a tour of a bunch of things that we're working on, that are just released, and kind of give you a view of where we see the vision for cloud modernization going. And if you take a look, a lot of you have probably in your organizations gone through a cloud modernization journey or going through one, which the first step is typically go containerize your workloads. Another step is going into microservice-oriented applications, breaking down the monoliths. And then another big step is going to serverless. And actually, that is the view that I've been driving in Azure since I started in Azure, is going, and Azure actually started in kind of the PaaS-y serverless with cloud services, but really going to you not having to worry about the infrastructure at all. And when you define an application, not having to worry about the details of the infrastructure. And so that's what you're going to see through this, is a big focus on things that we're doing to move us as far towards serverless as possible and to make it possible for you to actually easily develop containerized microservice-based applications that are serverless. So I'm going to break down the innovations into three different categories. The first one being containers, what we're doing to make containers better, specifically serverless containers and containers that you might be deploying on Kubernetes clusters that are non-serverless. And then I'm going to talk about things we're doing to improve the security of containerized workloads. And then finally, I'm going to talk about incubations. And I'll explain more about why I'm talking about incubations when we get to that section. So let's talk about containers. And how many of you are familiar with Azure Container Instances, ACI? So ACI, this is one of those places where Azure in the late 2015, 16, 17 timeframe kind of had this reputation of Microsoft's not the cool cloud native kind of company. But it turns out Microsoft were the ones that came up with serverless containers. And then you saw AWS and Google follow suit with their versions. We were first with this. And the idea here is you have a container image, you just want to deploy it and have the infrastructure worry about hosting it. You don't want to have to go create a cluster and deploy it onto these containers onto nodes. And one of the things that we've done is implement Hyper-V isolated containers with ACI. Because in Azure, when we talk about strongly isolating one workload from another, our security boundary is virtualization. And so when you've been deploying ACI serverless containers, you've been deploying them into Hyper-V isolated containers. Those Hyper-V isolated containers are running on a second level hypervisor. You can see in this picture there's a hypervisor on the bare metal, that's the Azure hypervisor, and then you've got a VM, and inside that VM there's another hypervisor, and that VM is creating these isolated containers. And that's inefficient, and if you came to my session yesterday, you know that we're going and working on implementing something we call direct virtualization, which is now we let ACI create these containers directly on the Azure hypervisor. And there's no intermediate hypervisor anymore, which, again, yesterday I showed all the benefits of that, from security to giving these containers direct access to hardware devices. We've also been making ACI more powerful, because it started out as single container instances that you could just go and manage individually. But just like with virtual machine scale sets, we want you to be able to manage groups of them consistently and scale them out and scale them back in and automatically update them with rolling update policies. And so we've introduced N groups, and I've demonstrated that at Build and last Ignite, the ability to go create whole fleets of a common ACI container instance image. We've also made it possible for you to connect a serverful kind of construct in Kubernetes clusters with the serverless ACI containers. Through Virtual Node, we introduced a long time ago, like 5 years ago, and then more recently Virtual Node 2, VN2, which now natively integrates with Kubernetes and basically removes a lot of the reasons why people couldn't use Virtual Node before, because now they look very native as the nodes to Kubernetes, and you get all the functionality and features that you would get with a full serverful node. Now, one of the things that we've also done is let you do these container instances with rapid scaling and bursting for AKS, but we've also recently introduced the concept of standby pools. And if you came to my session with Scott a little bit earlier, you saw me leverage ACI standby pools so that I could go bursting out to 100 container instances just in a few seconds. This is where you go create these images, you specify the standby pool parameters, and then as you're deploying ACI instances, it can go pull these things and then start to use them almost immediately by making them custom instances. ACI is the plan of record for Microsoft's internal infrastructure. We want to be serverless inside of Microsoft. And so over the last few years, we've been migrating more and more of our internal services onto ACI. So just to give you an idea that this thing is becoming the bedrock for Azure's infrastructure, and here are just some of the services. And it's basically like every week we'll find another service team that has completely completed a migration to Azure Container Instances. It's really exciting to see this kind of take off now organically inside of Azure and across Microsoft as well. So we want to make sure that there's no reason for somebody to not use an ACI container instance. When you take a look at virtual machines, or when you take a look at being able to deploy containers into your own VM or your own server, one of the benefits that you get is that the environment there, the resources, are shared by all the containers you deploy. And it's kind of soft sharing. Like one container can use a lot of memory, another one can use a bunch of CPU, and as long as there's enough total CPU and memory, you can have lots of containers in there kind of sharing resources. So one of the things that you can also do is a container running inside that environment can grow, basically use more memory, use more CPU. Now, when you want to do sharing in a hostile multi-tenant environment, you've got to be very strict about the resources that are assigned to one or the other. So we're working on a few things. One of them is resource over subscription, where you can actually put a bunch of container instances together and say, they're going to share a bunch of CPU. And here are the parameters for how they share. We're even making it so they can share memory. We're making it so that there's no reason for you ever to say, you know what, I want more control, so I need to deploy these containers in a non-virtualized way so that they can share and oversubscribe with one another. And one of the ways that we're also taking care of that and removing the obstacles is letting you stretch and grow container instances on the fly. So this is something that you're going to see coming out, which is stretchable ACI container instances. The idea here is you specify the min and max parameters for how big you want a container instance to be. And then on the fly, you can dynamically change how much resource it's got assigned to it, as long as it's fitting within this min and max. This is going to come with direct virtualization support for ACI, which we've already got enabled internally, where now you can put container instances together down on a single server and then have them grow and shrink organically. So let's go see a demo of that really quick. So here I've got my experimental container instance deployment of stretchable container instances. I'm setting min and maxes now for the virtual CPU assigned to them, and min and max for the memory. Here, min of 4, 20 gigabits max. Now I'm going to go and create that stretchable container instance in a few seconds. Here we go. And now I'm going to go get its IP address. And I'm going to do a load test on it to see what the performance of this container instance is going to be under a certain amount of load with Azure Load Test. So I'm going to specify that IP address of that container instance, load of 350 users, and let's see how that performs. So load test is starting up. And you can see on the top bar, load test is ramped up to 350 users. And on the bottom chart there, we see requests per second about 2.6 thousand requests per second. And then we also see some latency metrics. Now let's go and grow the amount of CPU and the amount of memory to 6 vCPUs and 12 gigabytes of memory dynamically. Say save, and that instantly applies, and you can see the load test still running. And we see the request per second now that it can handle jump to 7.7 thousand. And you can see that our response time also went down because there was more headroom for it to respond to all those requests. So now we've got kind of vertical scaling of ACI containers on the fly, something that is really a first when it comes to serverless containers in the cloud. So that's that section. So now let's go take a look at networking. In networking, we've got something called managed Cilium. And if you're managing your own Kubernetes clusters, you're probably using Cilium to manage network traffic among the pods in that cluster. And with Azure Kubernetes Service, AKS, you can bring your own Cilium. And this is what a lot of customers have been traditionally doing. If you take a look at the layers that are involved with managing IP tables to have those pods connect together and then talk across the Azure network if they're on different nodes, there's several of them there that with AKS with Azure Managed Cilium, which we introduced a while ago, are completely eliminated. And we also take advantage of Azure Boost to offload the network packet encapsulation and decapsulation of the outer packets that would otherwise be happening in software in your Linux host. And so this gives you performance plus security and observability. As everybody knows, that's what Cilium is really good for, is IP policies and routing rules, as well as traffic analysis and monitoring. And that's directly integrated into our tooling as well. But one of the things that we've recently done is bring Azure Managed Cilium eBPO host routing into Azure. And this kind of shows you our deep integration with open source. We're not only trying to pull the latest open source into Azure, we're also contributing things back to open source and the innovations that we develop ourselves. And this is a great example of that. Now with Azure Managed Cilium with eBPF host routing, you can see there on the left, again, there's multiple layers of encapsulation and processing of those packets in IP tables, which is very inefficient. And this is one of the benefits of eBPF, eBPF there on the right side with host routing, is that instead of IP tables, you're using eBPF functions. This is basically this is programmable code sitting right in the networking stack in Linux that can take and implement these policies and basically squash those two layers of policies into one program that implements them together. And so there's a big performance boost. So when you combine eBPF host routing with our integrations with Azure CNI and host networking and Boost Offload, you see some dramatic performance improvements. This demo right here, we're going to see 3 versions of Cilium. The left is bring your own, the middle is bring your own with eBPF, and the right is managed Cilium, Azure Managed Cilium with eBPF host routing. And we're going to run a networking benchmark here on all 3 of them. And you're going to see when they finish here running. And we take a look at the throughput, 6.53 gigabits per second on the left, 7 gigabits in the middle, and then close to 10, which is over a 50% performance improvement over you bringing it yourself without eBPF. And still a significant boost over you bringing your own with eBPF in it versus the managed Cilium that's built in. So this is the kind of integrations that we're doing deep with open source contributions into our stack to provide great performance for our Kubernetes pods. So next, let's talk about storage, because we got compute, network. Let's talk about an advancement we're doing with storage. And one of them that we've introduced is Azure Container Storage, which is built into AKS. And one of the things that you get out of Azure Container Storage with AKS is you get local and remote targets. So Azure disks or local NVMe drives. With Azure Boost, you're going to see this kind of performance, which I mentioned yesterday. There, up to 6.6 million IOPS for local NVMe access for your containers and 3 to 6 gigabytes of network throughput, of bandwidth rather. But one of the things that we're working on and we're going to come out with soon is in response to a lot of AI workloads and a lot of workloads that want to share images or data across a bunch of pods in the cluster. And that is distributed caching for Azure Container Storage. Let's say that you want to do model inference and you want to download a giant model. Well, how do you make sure that you don't have to download that model over and over again from Azure Storage to get it into your pods, where you can get it from local NVMe drives and locally cached. Of course, each node can go download it, but that's kind of a waste too, because another node wants it and they're going to have to go back to storage rather than maybe going right next door or right on the same node. The pod might be on the same node to go grab that. So let's go take a look at Azure Container Storage with distributed caching, loading a fairly large image. And this is going to be GPTOSS 20B, large LLM that's open source that we're going to go download from a container registry locally. And here we're downloading it. This is the non-cached version. We're going to fast forward here, and that took about 3 minutes to download. Now, if we see what's in there in our local storage and we delete that locally downloaded cache, we download it again, we're going to see that again, it's going to take over 2.5 minutes. So this is what happens when you don't have persistent caching or shared caching among your pods, is you're going to have to pay this performance overhead all the time. Now here we're on a different node, and we go and check what's in the local cache, and you don't see GPTOSS 20B is actually there, rather, because it's able to get it from the distributed cache that was downloaded on the left side. And so in this case, because it was downloading it from the cache from another node, it just took 24 seconds to go grab it. So this is the kind of giant performance boost that kind of surprising. Instead of going all the way back to storage, going back to the container registry, you get this benefit of just pulling it from the next door node and get it in just tens of seconds rather than minutes. So look for that coming soon. Now let's switch gears and talk a little bit about security, because container security is incredibly important. We're moving into a world where we need more and more deeper security. And one of the things that I love about containers is how declarative they are. They specify basically everything that's in this system. You also generally get exactly what's going to execute, or you can, and you get exactly its configuration, what devices it's going to ask to, what ports it's going to talk to. It's very unlike the kind of the world that we lived in traditionally of IT, of you just throw things in there and they're going to just party in some way, and you don't really know what's going on in those giant virtual machines that are running enterprise applications. This gives us the ability to be very prescriptive and lock down exactly what can happen. And that's going to make it more secure, because even if it gets compromised, a threat actor is not going to be able to do anything interesting because they're blocked by policies. Now, one of the things that we're doing inside of Microsoft is improving the security of Linux. Now, with no security controls applied to your Linux containers, your Linux hosts, you have this situation where you've got a binary and you want to run it. You can run it either in the host, or you can run it inside of the container, and it's not going to get blocked. So what a lot of people do is layer on security policies like SE Linux. You got a mutable host operating system. But the challenge with this is those SE Linux policies don't transparently go up into the container. And so while you might be blocking that image on the host, a container goes and runs that image, and it's allowed to. So one of the things that we've been doing is adding features and leveraging features to provide lockdown Linux containers. If you take a look at the stack on the right, you've got SE Linux, which we saw before. You also have something called DM Verity for your immutable image that allows you to specify policy about what can and can't run very precisely. And then we also have Integrity Policy Enforcement, IPE. IPE is a security feature for code integrity that Microsoft introduced in upstream. So this is now one of the core ways that people implement code integrity on Linux came from Microsoft. But putting these things together, we've got something called OSGuard. And OSGuard leverages DM Verity, like I said. And let me just explain what this is really quickly so you understand what you're going to see in the demo. DM Verity is similar to blockchain. You hash every block, and then you create this tree of hashes. So a group of hashes also gets hashed, with blocks of those hashes get hashed, and then at the root, you sign that root hash. So to check whether something is allowed to execute, you basically take your image, you create this dmverity hash tree on it, you sign the root, and now when a block gets read from disk, you simply go and say, okay, does that hash correspond to the hash of the parent of the slot in the parent block? If it does, you're good because you've already verified the whole tree. Or if you want to re-verify it again, you go up the tree and see if the hashes are all lined up in each parent block. Till you get to the root, and then you see if it's signed, and then you see if your policy says this signer is something you trust. So when you apply that dynamically, you get the ability to have these very locked down containers. So on the left, you see your container image registry, which has your container image manifest of the layers and the hashes of those layers. Then you have, associated with it, the dmverity hash blocks of each of those images. When you go deploy the container on the right, again, that immutable operating system with dmverity checking blocks as they're being read by the system against that tree and seeing if they're signed. If they are, you're good. And this applies to both the host as well as the pods or the containers. So what we're going to see here first is being able to download some malicious package, hello host, and that's in the host, and this is in the container. We're allowed to run them both, and this is the default, no security applied. Now, this view here, if you take a look at this OCR registry where we've got our image, we also have this manifest there, which has the layers that we trust, and the annotations that say the signature has to be this. So that's pulled down, leveraged by OSGuard. So now when we try to run that, we're going to get permission denied, and we go into the container, create the pod, and we're going to actually try to run it again, and we get permission denied. Because OSGuard with dmverity is checking and seeing this thing is not a part of the original dmverity hash tree because that block has been modified with the download, and so this thing is not allowed to execute. So very locked down images now, possible with OSGuard, which we're also working on upstreaming into Linux. And then we want to take this security a step further and get into confidential container groups. This is ability to have confidential containers, ones that are protected with hardware, that have policy associated with them for what can and can't run, where now you get policy enforcement plus hardware protection. So what I'm doing is pushing an image, and then I'm going to download it and run it and try to do things in this container that are allowed or not allowed by the policy that was associated with the confidential container image that's being enforced inside of that confidential boundary. And this is going to keep the security of that confidential workload, the data in it, and secure. So what we just got is an attestation of a hash from the hardware here and compares it with the hash that's in our policy, and they match. So this is a container that we trust. We're going to actually try to execute a command here, command/cdir, which the policy says is one of the commands that are allowed inside that container. And if we try that, we can see that it worked. And this is a Windows confidential container. This is something that is not out yet, but we're working on. And here you can see we tried to just do command without the /dir. Because that wasn't a command line that was allowed by policy, that was denied. And the idea here is now a threat actor can't go and inject commands into the container that might compromise the integrity or confidentiality of that container. And we can be very specific in the policy about what's allowed to happen and what's not allowed to happen. So this is where we're going with ACI and containers in general, is locking them down, implementing strong policies to prevent them from or protect them from outside influence. And now we'll get to a world where we know exactly what's running in it, what it can do, and threat actors will have much less elbow room to go messing around with things. We also want to make sure that we can fix vulnerabilities very quickly. And if you're used to fixing vulnerabilities in containers, you know that if there's a vulnerability in layer 1, like your distro, you've got to go rebuild all your containers that have a dependency on that image. And that means the sequential, go up the tree all the way to my application rebuilding, which takes time. And you got to push these things to the registries, pull them down, do another Docker build, push it up, pull it down, do another Docker build, redistribute these things all over the place. Huge delays, which could be precious if you've got an attacker that you need to defend against with a patch in hours, not days. So out of the Azure Office of the CTO incubation team a few years ago, we started something called Project Copa. The idea here is, what if you could slip a patch layer into it that's kind of like a hot patch? So you get your required updates, you create a patch image with those updates, and you just slide that on top of the existing image layering. And now when you go deploy that container, instead of seeing the unpatched binary, the workload sees the patched image from that layer that you injected. No need to go rebuild the whole list of layers. Now, of course, you want to get rid of those patch layers, so you go by your normal cycle of rebuilding things. But this lets you roll out a hotfix, basically, a patch, in like a few hours instead of days. One of the things that we're doing, though, is we've been patching our container images inside of Microsoft automatically in our registries and build pipelines using Project Copa. Millions and millions of container images over the last year we've been patching this way. But one of the things that we've not been able to do is patch runtimes, libraries on top. We've been patching the base OS distros. So we've been working on that as well. And what you're going to see here is us taking this to the next level and patching runtime. Specifically in this case, we're going to patch some Python packages. So this is Trivia Security Scanner looking at one of my containers. This is actually the Azure Cloud Shell container a while ago, which had vulnerabilities in it. Those two vulnerabilities, pip and requests, have vulnerabilities that have fixes for them. So what we do is set Copa patching, and we say we want to do minor level patching, and this is going to mount that image, pull down the packages, install them, and then create a new image, the patch image from that. So that's what's happening here. And now that's finished, and we can go and scan that image again with the patch layer in it, which patch the distro, all those vulnerabilities you saw at the top, as well as the Python packages that we saw, and look, all completely patched. No rebuilding of all the layers, just a patch layer, and we've covered the whole thing. So this is like game-changing when it comes to container security and keeping your container images patched. This is completely open source, so you can go even start deploying it yourself. Like I said, this is what we use in production in Azure to keep our images patched. So in the final section, I'm going to talk a little bit about some incubations. What you saw there with Copa is something that came out of the Azure incubations team. It's a team that I started 7 years ago. And some of the other incubations that have come out of that team that you might have heard of are Kata. How many people have heard of Kata, the Kubernetes event-driven autoscaler? So a few of you have. That came out of the incubations team. Dapper, the distributed application runtime. I've talked about that before. That also came out of the incubations team. So I thought I'd share with you, and by the way, Kata graduated in 2023. Dapper graduated about a year ago. And we've got some sandbox projects like Copa. That's actually out of my incubations team. And I'm going to talk about Radius, a sandbox project, and Drasi, another sandbox project. Because these are both, I think, very relevant for where cloud-native computing is going. Now, first one, Project Radius. And by the way, all of these are in CNCF. This is all open source. We're all developing this in the open. Feel free to contribute and contact us and reach out if you'd like to start a project in your company with one of these. But Radius starts with this looking at what Kubernetes is. And Kubernetes is, or applications, cloud-native applications are more than just Kubernetes. If you take a look at a cloud-native application, they're using lots of different resources. They're using cloud services. They're using configuration settings. They're using infrastructure, volumes and secrets and pods. And so the problem with Kubernetes, and it's a great infrastructure platform, is it's really infrastructure focused. It's not app focused. And so if you want to define an app, you're basically merging your definition of an app with the infrastructure it runs on. And the idea behind Radius is separating the app from the infrastructure. And there's a lot of benefits that come out of modeling an app separate from the infrastructure. Like with Radius resource types, you can model any resource. And built into Radius is support for AWS, as well as Azure resources, as well as many Kubernetes resources, just out of the box. But you can go define your own. And you define them at the level of your app devs and what they care about. But then your operators can define what are called recipes. And the idea behind a recipe is that given a Radius type, a recipe specifies exactly how that type gets deployed into an infrastructure. And you register your recipes in an environment. And you might have a recipe for your prod environment, for how that resource gets deployed there. And that same resource might have a different recipe for deploying it into your dev environment. And then one of the things you get out of this when you deploy and you model things this way is you get secrets taken care of, connection strings and connections and managed identities are taken care of for you. The developers don't need to worry about all that infrastructure, and neither operators don't need to specify everything because Radius takes care of it. And you also get this graph out of it because you've modeled it as a Radius application with resource types and the way that they relate to each other. When you go deploy it, you can see a graph of your application, which has been something that's also missing when it comes to looking at the world as infrastructure, which are just lists instead of graphs. So just to give you an example visually here, we've got this application, a gateway, a front-end container, a back-end container, Redis cache, and MongoDB. Very kind of typical three-tier application. And with Radius, what we do is define the application that way, and then we create an environment with the recipes for how it binds to a particular infrastructure. In this case, the recipes specify how to bind it to Kubernetes. But then we can create a different environment with recipes that bind it to Azure, and using Azure versions of those resources. We can then swap out a different environment with different recipes to bind it to AWS. And to deploy that app, we didn't have to change anything about them. We just pointed at an environment with the recipes, deploy it there, and Radius takes care of the rest. So again, separating the app from the infrastructure gives you this out-of-the-box portability, if you want it, but gives you the other benefits I talked about as well. So if you take a look at everything that Radius is, it's the Radius types plus the infrastructure recipes, this Radius universal control plane. You could actually, with Radius, take an app and deploy parts of it to AWS and parts of it to Azure, and parts of it even to Kubernetes on premises, just with one application definition. Because the Radius universal control plane knows how to talk to these other control planes, Kubernetes, Azure, and AWS. So what I want to show you, because it has to be AI relevant at this point, is how you can take an application that off the shelf and ratify it in a very straightforward way to separate the app from the infrastructure such that we can take that app, apply governance to it, and deploy it in different ways. And we thought we'd just take one of these Azure samples. This is an Azure sample chatbot app that we just went and said, hey, let's go take a look at that one. It's an insurance chatbot. And that chatbot has 2 agents in it using semantic kernel, each one talking to OpenAI, and then it uses a SQL database to store embeddings. And here's their repo if you want to go check it out. This is the non-ratified version of that app. But we went and ratified it, and the way that we did that is first we containerized the app. So the semantic kernel plus the functions, those agent functions, put them in a container. Then we created environments that you're going to see, but we created recipes, defined recipes for creating those model endpoints that the app could use, as well as the database as well. So we're creating a couple of custom resource types, one of them for the OpenAI connection, and one of them for the database connection. So let's go take a look at that in action. Now here's the Radius dashboard for a Radius deployment that I'm managing. And here's my resource types that I've got registered in this environment. One of them is AI models, and the other one is the SQL Server databases. If we click on AI models, you're going to see an example of how you would configure one of these resource types that we've custom defined. This supports a bunch of different OpenAI models, embedding models, and LLMs. And if we click on the database, this supports different sizes for the database, which matters. Now we're going to look at how this app, the container, sets up connections to these different services right here. We've got 3 different resources that the app connects to. And again, Radius, I know this is a little fast, but Radius is going to take care of connecting it to those resource types for us. Because it's separated from the infrastructure, I can literally take containers can be mapped to infrastructure hosts, and we've got ACI and Kubernetes. So this code looks exactly the same, except one is going to deploy, one of these environments is Kubernetes, and the other one's ACI. And I'm going to deploy the app to both of them. And on the right side, we've got our Kubernetes deployment. Well, first, I'm going to show you the app graph that you can see here, exactly what that app looks like from a Radius perspective. But here's on the right side, the AKS deployment, on the left side, the ACI deployment, the resources. And we're going to cube cuddle exec right into that chatbot app on the right side in that Kubernetes cluster, and we're going to go to the ACI and connect to that ACI container here in the browser. And then you can see interacting with the chatbot, and it works exactly the same way on both sides. Again, the point here to emphasize is that I've got this containerized app with ratified resources, deploying it to different environments, and I didn't have to change the app at all. And I also got to see a graph that Radius knows about that app. But Radius also lets you do governance. So what if I wanted to, in my environment, have different rules for different deployments of that app? Like in my test environment, I'm OK with using the basic SKU. I'm OK with not having features that might be expensive that I don't really need for testing turned on, like multi-zones off, disaster recovery's off, jailbreak filter is off so that my devs can have some fun while they're developing this app. Okay, that was a joke. And then in my production environment, of course, I don't want end users to be jailbreaking it, so I've got a jailbreak filter on. I've also got disaster recovery and the other things that I want for production deployment. So let's go see how you can set that up very easily with 2 different environments. And on the left side, I've got my prod environment. On the right side, I have my dev environment. And now I've got on the left side, P1 SKU, on my right side, the basic SKU, and then with the other differences that we talked about. And I've got jailbreak filter on the left and off on the right. So I'm going to go deploy each one of these. And this is, again, showing you how the ops people that care about what's going on in these environments can set what they want, the policies they want, without having to mess with the app in any way at all. And we can see in the prod environment, I got my P1 that I configured. In my dev environment, I've got my basic SQL Server pricing tier. And I've also can check to see if the jailbreak filter is enabled. So if I go and launch the chatbot on both environments, on the right side, I tell it to ignore all policies, and it's like, sure. That's because it's the dev one without the jailbreak filter. On the right side, you can see that it gets flagged as a jailbreak violation. So very easily, separation again of dev concerns from operator concerns, app definitions very clear from the infrastructure definition with Radius. Now the last incubation I'm going to talk about is Drasi. In Drasi, the idea here is, as we move into more event-driven style architectures, one of the things that's really challenging about responding to events, especially in complex systems where we're worried about state changes, is how do I get the changes into my app, my logic, and then how do I keep track of the state so that I know when something should happen? And then how do I trigger that to happen? And up to now, there's architectures that have to poll, so go read the thing over and over. Did something change that I'm interested in? Or you do changelog event processing and have this very custom logic to go looking at the events and saying, is this something I care about? And if it is, oh, did it change? Did it trigger a state change that I'm interested in so that I can then react to it? or you do streaming analytics kind of on the streams as you're processing. This ignores even the fact that at the end, you've got to figure out how to keep track of that state. Like, if this value is below this threshold for 5 seconds, and this one's above this threshold for 2 seconds, and this is also true, then I want to do something. And while that expression that I just gave you might be relatively easy, think about more complex ones and think about changing that over time as the requirements change. And what happens if one set of state is in a Postgres database, the other one's in a MongoDB, and you've got to join them together? That's exactly the kind of problem Drasi's designed to simplify. And when I say simplify, I mean drastically simplify. Drasi's concept is very straightforward. In the middle there, you've got continuous queries. You can think of those state changes I was just describing as just a database query. In fact, we've decided that graph database queries are the best way, the most flexible way to describe these kinds of things. Because those conditions I just described, you can map that directly onto something like Cypher or GQL very easily. If this has been like this for more than 5 seconds, this is less than this for 2 seconds, and so on. And then all you have to do in Drasi is say, when that condition is true, go execute this reaction. And that reaction can be fire this webhook, put this message in an event hub. It can be do a signal R message. It can be anything you want. And likewise, on getting the data in, anything can plug into Drasi and feed it data. And that data, it comes in as a stream of messages. So it's designed for continuous change data sources. And Debezium, which is an open source continuous change format, it supports natively out of the box. So we've got tons of different sources that we've implemented, tons of different reactions we've implemented, and then, like I said, Cypher and now recently JQL as the two languages you can use to describe your continuous queries. See, Postgres, Cosmos DB, Microsoft Dataverse is new, so supporting AI workloads with this. And then you can see a whole bunch of the reactions I mentioned. So what I'm going to show you is another AI-centric. Like, you have a bunch of data moving into a rating system for your products. You want AI to be able to query the ratings and answer questions about those ratings. Now, keeping that vector database up to date with the changes can be tough, but Drasi is going to simplify that. So let's go take a look at this demo here. And the first thing we're going to look at is the sources. We've got two databases we care about, a Postgres database and a MySQL database. And one of them has the products and the other one has the reviews. And we can take a look at the products. We've got a bunch of products in there. And then we can go take at the reviews that customers have left for specific products. We join them by the product ID. Now we go and say, this is the query that we want. If it has a review, we want to emit a new review. We want to emit the name, the review, and so on. And now we go and we can take a look at the current state of those queries. We see a bunch of new reviews that came in. And we can ask questions now because those were embedded about which laptop has the best reviews, which ones do you have. And you can see there's two products in the database. And by doing that continuous query, we know which one has the best review. Now I'm going to go and take a look at when a new review comes in, we're going to take the data that comes out of that continuous query and go embed it and stick it in this embedding database, the quadrant. And we're going to use this text embedding 3 large model to do that. And now I'm going to go and look at what's in the quadrant database, and you can see there's 9 entries that have ratings. And I'm going to insert 10 positive reviews for that new database, that new laptop by putting that in the database. All of that just flew through Drasi. And now if I ask what laptop has the best review, it's going to tell me, actually this one that we didn't see before, Gamer X Elite, has the best reviews. So just let me stop and summarize what you just saw. All I did was specify those two source databases as my sources, this graph query as my continuous query that said when a new set of review comes in, go and send it to this reaction. And that reaction took that information and embedded it and put it in that database. And I didn't have to do anything. No polling. My join was in that query. It's completely standing, yeah. So it's, and I think this is transformative because the things we've been able to do with Drasi, like you can create with SignalR web pages that are the real-time view of complex, very complex systems with very complex changes. And we've been doing things like adding a whole bunch of support for like, hey, something hasn't happened in 10 seconds or something's missing. And so really rich queries, operators that we've added that let you do a lot of really cool event-driven stuff. So that brings me to the conclusion of the talk. Whirlwind tour of some innovations that we got in containers and container instances and serverless, storage improvements, networking improvements in this, the containerized stack, security features including patching and confidential containers and immutable images, and then finally incubations. And again, I think one thing I want to emphasize about this whole thread through this is open source. Everything you saw here is open source. Either we've pulled from open source or we've given back to open source or we're developing in the open. And so that's kind of, in a nutshell, what we're doing with cloud native incubation is open. So with that, I want to thank you very much. Hope you had a great session, saw some stuff, and encourage you to come and contribute to these projects. Thank you.